This conference will now be recorded.
Hello everyone, welcome to our webinar on modeling of car cabin acoustics using COMSOL Multiphysics. My name is Arpad Forberger and I'm an application engineer at Gamax Laboratory Solutions Ltd. Today we are going to take a look at the software and see how to set up physics for acoustics problems. I will walk us through some models to give you a chance to see the software up close and see how it might help you in your work. Today's outline looks like, why should we do simulation at all? So let's find out some answers for that. The car cabin acoustics overview, what the model setup looks like, what sorts of simulation methods are available with advantages and deltas, all of those, what you can do with the CAD and the mesh in COMSOL Multiphysics, what sort of boundary conditions and material models can be used to set up your physics. What sort of sources can you use in this acoustics simulation? And I will show up the model live in COMSOL Multiphysics. And the second part will be a concert hall model where you can see how the ray acoustics feature can be used for larger acoustics simulations in COMSOL Multiphysics. So what is COMSOL Multiphysics? COMSOL is a multiphysics modeling, simulation, and application design environment where all of the steps of a simulation are integrated into one user interface, from the initial setup to the solvers to post-processing to putting together a custom-built application. A COMSOL model allows you to couple together physical effects the way they are in the real world, which we refer to as multiphysics. Once you have completed your COMSOL simulation, the software also allows you to create a result to collaborators, customers, or even colleagues around the world. This is our product suite. We have add-on products that can be combined with the COMSOL Multiphysics core package to enable simulation of specific physics phenomena across a range of application areas. These can all be combined with each other. We have modules for electrical, fluid, heat, mechanical, acoustics, and chemical simulations, as well as several multi-purpose modules and tools for interfacing with external software. COMSOL is very flexible. It contains many predefined physics interfaces, but also allows you to define your own custom physics and equations. So why do we need simulation? What kind of benefits do we have if we do software simulations? So you can do some sort of virtual prototypes, which can be faster and cheaper than building real-world physical prototypes. You can do measurements like in a real situation, so you can use built-in post-processing features to have a look of the sound of a car cabin or any acoustics related problems. You can visualize, you can get the know-how of your physics, and you can get a much better in-depth look what you would like to do with your acoustics devices. So this is our setup. So this is a sort of car cabin acoustic simulation. We have different boundaries, different materials, different material models, and we have some sound sources located at different parts of the car cabin. And we want to solve this model for a set of frequencies to get a result on the acoustic field and the sound pressure levels at different locations in the air domain. There are different methods in COMSOL Multiphysics that can be used and combined to get some in-depth look of this acoustic simulation. There is the well-known finite element model or the boundary element model that can be used. There is the so-called discontinuous Galerkin finite element model if you would like to do transient simulations, some sort of And you can use the ray optics or the ray acoustics feature that we will use in the second model, where we want to solve for higher frequencies. From the boundary condition perspective, you can use simple normal acceleration boundary conditions, or you can use lumped methods and sources to place speakers inside your car cabin. And you can use frequency domain solvers, or you can go to the time domain to get some sort of simulation results there. So this is the finite element method and the finite element mesh. We will use this for our model, and we will open up soon to see what the solution looks like. It has its own pros and deltas. It's very versatile. You can use with any other physics, so the full multiphysics capabilities can be used, and it's easy to parallelize. But on the other side, it can be a large model. You need to resolve the wavelength well to get proper and nice results. And of course, for larger models, the memory consumption can be huge. Some examples that include the finite element modeling besides this car cabin simulation can be like the full harmonic distortion model of speakers, loudspeakers, or the acoustic impedance calculation of grills and other miniature acoustics devices. Other feature that can be used in COMSOL Multiphysics is the so-called boundary element method, which has some advantages on or over the finite element method. One is that you don't need to create a volume mesh, only a surface mesh is needed for such a simulation. You can use also some multiphysics couplings to get an insight, but on the other side, it can be much more computational heavy to get the results. And if you are looking for the solution for higher frequencies, like you would do in a concert hall or even in this car cabin simulation, you can go for ray tracing. That's a new feature in COMSOL Multiphysics, and we will utilize this to get an inside look for this concert hall. And there are some time explicit methods like the discontinuous Galiarcing. So if you want to look into the time domain simulations, you can also use this feature and get an insight of your acoustic field in the time domain. So depending on the frequency range, there are multiple choices for low or mid frequencies. Like with the car cabin, we will use the finite element method, and for higher frequencies, you can go for the ray tracing method. From the CAD part, you need to remove as much details as necessary to get a better mesh, but still enough resolution for the wavelength. And we want to solve and validate on the sound pressure level at different locations in front of the seat, on the front seat. So we will use this at the post-processing part to see what the result is. And now if we go to COMSOL Multiphysics, we can go into the geometry and the details, what we can see here. So we have this car cabin geometry with the 4 seats, different setups for the glasses and the dashboards, and we will use some of the grills and holes for placing the boundary conditions there. So we can get an inside look how this looks like. So this is our geometry. So from the absorption coefficients of the materials, these are frequency dependent. So we can plot these properties here. That's for the carpet. As you can see, it's not a constant value, but function of the frequency. The same goes for the seat. So the absorption coefficient for the seats also varies with the frequency. From the physics, we have pressure acoustics, frequency domain, physical setting set up here for all the domains. And we have the so-called impedance boundary conditions for the different setups. We have, for the roof, we have a so-called porous layer. That's the setup here. And the same porous layer boundary condition is used for the floor. And for the seats, we have a simple impedance which is a calculated value based on the absorption coefficient that we imported as an interpolation table. From the materials, we have different materials, like in a regular car, we have glasses for the windows, aluminum parts for the shells of the chassis. We have some nylon parts for the dashboards, plastics for the outer surface of the suites, floor material, of course, air, like the inner domain, and the roof material, which is a different part, which is a porous material. From the study node, we have a frequency domain solver from 100 Hertz to 1000 Hertz, and we store the solutions at every 100 Hertz to get an inside look how the sound pressure changes at different locations. So if we plot the acoustic pressure, we can see how does it look like inside our car cabin. So for 300 Hertz, this is the sound pressure level. This is how it looks like. And we can also plot the sorry. So this is the sound pressure level plot with different frequencies. So if we go to the first part, which is 100 Hertz, we can see some standing waves forming inside our cabin, and we can plot the result for different frequencies for 200 Hertz, 300 Hertz, and so on. So this is one thing. We can also plot the intensity, so how it travels, how the intensity varies inside the car cabin. So we have higher intensities at the loudspeakers that are placed close to the legs of the seats on the front seats. So these are the sound sources. So we have higher intensity there, and as the sound travels around the sedan interior, so does the intensity decreases. And we can plot the response at different locations. So we have this cut point data set here. So we have defined these data points with these 2 points, which is in front of the front seat. So we can store these coordinates and plot the pressure change at those locations. And if you have some results from measurement from an acoustic chamber, you can put those measured values onto this graph, and you can compare the results with those. The second model looks like a small concert hall. So it's a bigger scale. So we have some frame here. We have some, So we have some diffusers, we have some glass walls, we have some seats with different absorption coefficients, and we want to plot the reverberation time and the response at different locations at the concert hall to get an insight how it looks like. So if we go to the physics settings, here you can see that we have the door, windows, all of those boundary conditions with different properties. And we have a virtual receiver. It's not physically defined, but it's used at the post-processing part. So you can use this so-called receiver data set to see what the result at the frequency, in the frequency range. So if we go to COMSOL and open up the model, we can see the boundary conditions and the response plot at those locations at the stage. So as previously, we have the absorption coefficients as the function of the frequency, different values for the walls, for the windows, floor, for the side diffusers. All of those coefficients are the function of the frequency. Then from the physics part, we have the ray acoustics domain. As you can see, it's not selected because we are using only surface meshes. So here, no volume mesh is generated. So it's super easy to solve. You need much slower memory, a lower memory consumption than you would need for a full finite element model. So we have walls, and we have different boundaries with different boundary conditions. So except the diffusers, we have this specular reflection everywhere as a boundary condition, and the coefficients, as we have seen at the first plot, they are a function of the frequency. And the same boundary conditions go for the floor, entrance, windows with different absorption coefficients. And for the diffusers, a so-called mixed diffuse and specular reflection boundary condition is used. And we have the seats, absorbers, and we have this cross-section where we want to capture and calculate the sound pressure level. So a sub-node is added like this one. So the sound pressure level calculation is active on this surface. Release from grid, we simply define the point where the source is, what kind of source it is. It extracts in the spherical direction, but it can be an arbitrary expression, hemispherical, or whatever you would like to add as a source. And we have a ray termination feature. So if the intensity of those specific rays go below the threshold, they disappear. So it helps the computation to make it much faster. And from the mesh side, we have only a surface mesh. So if we remove some of these walls, you can see that there is no volume mesh. Only surface mesh is used since we are using this ray acoustics physics interface. And from the ray tracing solver, we are solving for time steps. And we can plot the ray trajectories and different time instances, how the rays travel. So we can go back, that's the initial at 0 time, and then at different points in time, we have different locations for the ray sources. And what is most important, we have this so-called receiver dataset. So we can define a virtual receiver, microphone, anywhere in the computational domain, and you can calculate the response from the source, and you can plot that one. So you can calculate the reverberation time. So if you have some analytical closed form calculation, you can plot that also, and you can plot on top of that what you have calculated in COMSOL Multiphysics. So this is the reverberation time in the frequency range for different models. And you can also plot the FFT of the impulse response. So you can use an FFT calculation on the desired data set, not just the time-dependent simulation. So it's easy to do that on top of the time domain analysis. Until it is evaluated, we can go back to our model to let's see what else do we have here. So here is how the model is set up. We have a ray acoustics feature. We have absorption coefficients that are functions of frequency. We have different boundary conditions for the different domains, for the different surfaces like the entrance, floor, and diffusers. And we have some release from grid subnode where the rays are released in different frequencies. And the absorbers, we use a mixed formulation, the so-called mixed specular and diffuse boundary condition. And since we are not meshing the internal air domain, you can include the absorption of air at the post-processing part. So you can take into account the attenuation which happens in the air domain. And here are some results for the wave trajectories and from the impulse response. So it's a time domain calculation, so you can plot the result like pressure variation in time at the receivers. Those receivers can be anywhere in the domain. These are just virtual, so-called virtual receivers or microphones. And what we are calculating is the FFT of that response that we are waiting for to be evaluated. And of course, you can plot the sound pressure level at anywhere in the domain where you have added that sub-feature. So if you are looking into some sound pressure levels inside the concert hall, you can use that at several frequencies. So if you are looking for higher frequencies, this Ray acoustics physics interface can be used. And if you are working with the lower frequencies in the lower frequency regime, you can use either a finite element method or boundary element method. Or if you have a multiphysics problem, you can couple all of these together to get a true multiphysics problem. Okay. And some other sources that you can use in COMSOL Multiphysics. It's not just room acoustics. There are other functions and other fields where you can use COMSOL Multiphysics and the Acoustics Module. It can be used for instruments like the sound propagation in the violin and how the sound will look like, or you can use in automotive mufflers, in muffler design, so you can tune the sound of these devices. And of course, you can use in ultrasound measurements. If you have an ultrasound flow measure device, you can use even the time explicit method in COMSOL Multiphysics. You can access and you can ask for this COMSOL News magazine, where you can have more in-depth information about these features and other forms of COMSOL. So this wraps up my demo. Thank you for listening and see you at our next webinar.